I want to introduce you to the idea of projections, projection of one vector onto another, because this is a really useful technique when we come to finding distances in geometry problems. And the way to think of it is a projector is usually when you're shining light onto a screen, and that's an image that I want you to have as you think through this. So in each of these examples here, I'm going to project the purple vector onto the red vector. So the red vector is acting like the screen, if you like. What I'm going to do, I want you to imagine that I'm projecting light at a right angle towards the screen, as you would do if you're projecting a film. So I'm projecting light directly onto the red vector, and the projection of the purple vector then is just the shadow that it creates. So if I'm shining light like this onto the screen, then the shadow that is caused by the purple vector would go along to here, to the point where that makes a right angle. And so the projection of purple onto red is that length there. The projection is a distance, is a length. So think of it as the shadow cast when you're shining a light onto the vector you're projecting onto. So if I look at this example, I want to project onto the red. So I'm going to, this time I'm going to project light perpendicular to the screen. So I've got to think, where will the shadow fall? So in this case, I can see that the projection is this one here. When the angle is wider, the projection is shorter. Seems to make sense. So that will show up in the formula that we derive shortly. These examples, interesting. Again, I'm going to project the purple onto the red. Now, even if the red is very short, the light is going to continue coming. So in this case, okay, I'm projecting at right angles onto the red vector. So I'm going to project. The end of that vector is going to go to there, forming a right angle again. And so the projection this time is this. So the projection can be longer than the screen, if you like. The projection there, the distance is longer than the magnitude of the red vector. In this example, I've got the purple vector, the angle between them is obtuse. But the screen, imagine the screen continues backwards. So in this case, the projection, let's project vertically, or sort of perpendicularly onto the screen. So that light would come there. And so this time, the projection is here. So that's what I mean by the projection of one vector onto another. And what we're going to do is derive a formula for finding that quite quickly. So let me just move that up a little bit. And let's get the diagram set to go. I'm going to take vector A and vector B. Here we go. An angle theta in between them. And I'm going to project A onto B. And let's just go through what we did. Project onto B. So that's where the shadow would fall in here. So I'm actually talking about this distance in there. Now I can see from this diagram that that distance is equal to the length of the hypotenuse times the cosine of this angle here. So it's magnitude of A cos theta. Okay, we've got that. But I also know from my previous results that cos theta is A dot B over magnitude of A, magnitude of B. So I can see by multiplying up A cos theta is equal to A dot B over the magnitude of B. And so I can put this result into here and conclude that the distance, the length of that projection is actually A dotted with B divided by the magnitude of B. And so the way that I remember that is that let's put this as a final result, the projection of A onto B is equal to dot product of both of them and divide by the magnitude of the vector that you're projecting onto. Okay, so that's the result that we're going to use when we talk about projections. And if you start to think about this, you can see that the bigger the angle, the smaller the projection is going to work out. The length of the screen is factored out by the fact that you divide by the magnitude of the vector you're projecting onto. So a very useful formula, as you will see over the next few lessons.